Greetings. So the main purpose of this video is to remind myself of the function I added a while ago in OEIS. And also for people who have never heard of this kind of thing, it will be a good intro for Dirichlet generating function. The main purpose of this sequence is to express the Riemann zeta function to the power of 3/2 as a sum. It's the same as the original sum, but instead of 1 in numerator, everything should change to some other number, like we call it A2, A3, A4, and so on. And this sequence listed all the denominators of such A1, A2, A3, A4, and so on. To make such computation, if you go back to Wikipedia and looking for the definition of Riemann zeta function at the beginning, you will find it's hopeless to do anything useful from that. So instead, we need to use the Euler product formula for the Riemann zeta function. So instead of making the sum, you have equivalent form that the Riemann zeta function is a list of product of all 1/1 minus p to the power minus s, where p is all the primes from 2, 3, 5, 7, 11, and so on. So you can see that on the line lower than the cursor I'm pointing at, it does show all the expansions. And this is infinite sum. So you want to make sure you include all the primes. And this is the place that we start. Let's go back to our formula. So here is 1/1 minus p to the power of minus s. It's transferred to 1/1 minus p to the power of minus s. And the whole thing raised to the power of 3/2. Okay, then let's go back to the notebook, and you can see that I do have a term that's 1/1 minus x to the power of 3/2. So in this case, you don't have to write the p to the power of s explicitly. You can simply use x. And if you expand it, this is a series function, gives you the Taylor series of this expression at x equal to 0 and the rise to power of 20. So now let's just take a quick look at the actual example. So the formula looks like this if we reattach x to the right-hand side of each coefficient. Here we'll use 100 as the concrete example to show you how the computation is completed. So if we factor the integer 100, it looks like 2, 2, and 5, 2. What it means is 100 equal to 2 to the power 2 times 5 to the power 2. At this moment, we can plug those prime numbers back into the Taylor series we had above. So for x equal to 2 or p equal to 2, we can just put 1 plus 3/2 times 2 plus 15/8 times 2 to the power 2, ... Notice that I do not have p to the power of minus s here. The minus s will be carried directly into the 1/n to the power s term, and will not affect our an terms. And we can do the same thing for p equal to 5. So a100, the coefficient of 1/100 to the power of s, is simply the product of the coefficient of 4 and times 25. In this case, just the multiplication of the third items inside the two series. So let's break down these steps. So assume we already extract the 2, 2 from the list above. So we can directly plug this value into our functions. And we add 1 to each element using syntax sugar to make sure that we extract the third item from the Taylor series above. Okay, let's also check. We indeed using the proper index, and then we plus times at around the list to convert it into a product. And this is the coefficient that we are looking for. So the denominator of this value should be 64, but you will not see that in the list we have here, because the term in the OEIS file, it is only 77, so we need to increase it to 100. So the 100 term is exactly that one we need. And we can also easily switch this function to extract the numerator for us. We simply replace denominator with numerator, and we rename this function. Okay, let's do that again for number 100. And you can see that this number is 225. That's exactly what we need. Okay, that's everything for this function. Thanks for listening. Bye-bye.